Record on now. Okay, so what did we just see? So last hour we've seen some distances on between probability distributions, right? So we have this simplex on which probability distributions. I believe it's always nice to write it with 3 outcome distributions, right? So we have P and Q, and we've seen some distances. So there is this trace distance and the fidelity, which is not really a distance, but it kind of can be related to some distances, right? So P and Q, as I leave here. Okay. But now we are doing quantum information, right? So actually, kind of the probabilities, they describe some states of classical systems, right? With uncertainty, obviously. But we deal with density matrices, okay? So we now have also, we'll consider the similar situation, but with density matrices. So, for example, we have 2 density matrices, sigma and rho, and they live, for example, in the case of qubit, they live in some log sphere, right? In general, it's some other convex space, because we always have the boundary, which is a pure state, and all the inside is a mixed state. And again, we can also define some distance measures between quantum states, right? And see how to interpret them. Actually, today, I guess we only have time to see the trace distance. But just before, the general thing is that, I guess you agree with me that kind of quantum formalism should encompass the classical formalism as a particular case. This is sometimes referred to as the correspondence principle. So for example, if you have 2 states which commute, right, then we can write them together in the same basis, right? So for example, we can diagonalize this one, and this will be like Pn, I don't know, and the sigma will be Q1 to Qn. This is just diagonal states, right? But really, because they commute, they kind of all commeasurable, so we can diagonalize them on the same basis. And actually, this case here should kind of correspond to the case of classical probability distributions. Do you agree with this? Because again, it just describes a mixture of n disjoint possibilities, exactly like here. Here we describe a mixture with some probability of occurrence of n disjoint probabilities. And in particular, if we measure in this basis which diagonalizes them both, then we exactly just get these probability distributions which appear here on the diagonal. All right, so when we construct the distances on the states, it would be nice to just we recover the classical distances in the case of commuting operators. Right, so this is kind of be the starting point. We just start with these things and then see how to generalize it to general states, which don't necessarily commute. But we can keep it in mind in the back of our heads, this correspondence principle. Yes, so then we start with just describing the trace distance. So kind of the quantum trace distance. Okay, so I will just, okay, so 3, this will be distances, distance measures between quantum states. And first we'll just see trace distance. Actually, this is why it's called the trace distance, I guess, that's one as well. All right, I know it under this name. So we'll just give you the definition directly. So for 2 density matrices, so for two states, rho and sigma, so just given by 1/2 of the trace of their absolute value of the difference. Okay, is it clear what this means? So you see this is an emission operator, right? Here, so I can just diagonalize it, and the absolute value is just taking the positive part. So negative eigenvalues just become positive, right? And then I can just trace it, and this by definition gives me the trace distance. So first thing we can check, okay, we can check that it's a distance, in the sense that this thing, maybe we can do it in the exercises. So actually maybe we don't, because we will recover it at the end by connecting it to the classical trace distance. Okay, first thing we can check is that for the diagonal states, it's indeed the same. So for states which commute, it's indeed the same as the classical trace distance. So let's just do it. So we just consider commuting states. Commuting states, rho and sigma, and then we have just a distance between rho and sigma is just a trace distance between these matrices, P1, if we express them in this basis, right? 1/2 Q1, Qn. Okay, I hope you see it. Well, and we can just write it down, and this is by definition 1/2 of the trace of the big matrix, which just has P1 minus Q1, P1 minus Pn minus Qn, all the differences here on the diagonal. All right, and the trace of this is, of course, so the absolute value of this matrix is just putting the absolute value inside. Okay. In other words, this is just 1/2 sum of the absolute value of Pi minus Qi, right? So this is precisely equal to the trace distance we just defined last hour between two probability distributions, which is nice. Okay. Good. Now, does it have the same meaning, or does this trace distance have the same meaning as the one before? So to answer this question, we can first see how it connects to this classical trace distance, right? So in other words, like kind of the quantum, in the quantum case, we have kind of this distributions rho and sigma, right? And the trace distance, which we just defined, right? And in the classical case, so the case of probability distributions, we just have two probability distributions, PQ, and the trace distance between probability distributions. But now, of course, what we can do is we can kind of take these two states and apply some measurements, right? So we do a P of M given by some elements at Ek. So we will define it again as before. We can just define Pk is equal to trace of rho Ek, and Qk is equal to trace of sigma Ek. Okay. So there is always a way to go from the state. By fixing the measurement, we can go from two states to two probability distributions, right? And the question is how these two distances relate. Okay. Basically, what we want to show is that this thing corresponds to the best case of this, right? Then it will inherit all the interpretation we had from the from this trace distance. Okay, so let's do it, and let's show this, right? That this is actually equal if we optimize over this POM. How to do it? Well, it would be nice to keep it, but no space. So to do it, we just consider for this operator, right? So we'll keep for the definition here. So we have d of rho and sigma. This is 1/2 trace of the difference. Okay, so now consider this rho minus sigma. Okay, operator. Consider rho minus sigma as an operator. So of course it's Hermitian, of course, right? So since it's Hermitian, I can diagonalize it. Operator. So since it's Hermitian, in other words, it's equal to rho minus sigma conjugate, adjoint. There is a basis. There is a basis where it's diagonal. It's diagonal. Okay, and then it means that in this basis it will be expressed like this with some eigenvalues here. So lambda 1 up to lambda n. In addition, we can actually just kind of fix the basis in such a way that we just rearrange these elements so that all the positive eigenvalues can come first. So plus, right, up to, for example, Lm plus. So here we'll have all the positive eigenvalues first. It's just a matter of arranging them as we wish. And we'll have all the negative eigenvalues coming later on. So this will be minus lambda minus 1 to minus lambda minus the last negative eigenvalue, right? Which is very useful decomposition, actually. Because we can also now define what we'll define. We will also define our two operators. So we'll define just this thing as a sum of two things, which are orthogonal, so which are block diagonal. Now the nice thing here is really this block diagonal. So here are just zeros. So we'll just write this as equal to P minus Q, and P and Q are just these parts. So we have P is equal to lambda plus 0, 0, right? All of them. So 1 to the last one, and Q is equal to zeros in this block. And minus, minus plus lambda minus here. Okay, clear. Okay, so now, in other words, we just see we have this now P. So okay, just write it down. So it has this sigma minus rho is equal to P minus Q, where these guys are log diagonal. Okay. So now let's consider the classical probability distribution for the POM, for some POM. So this is given by sum of 1/2, sum of this trace, right? Well, let me just, no, I think it's, I'll just write down the big thing. So it's, okay, I'll just start. So it's PK minus QK, right? This is just a definition. In other words, it's 1/2 sum of trace of EK of rho minus sigma, right? This is just the same thing. This PK by definition is the trace of this on this. Okay, now of course the trace is linear, so I can put the sum inside. You agree with this thing, I guess. No? All right, now we'll just use the same decomposition here. So this is 1/2 sum of trace. Okay, of the trace of EK P minus Q. Easy, so this just another line. We'll just see where I want to go with this. Trace of EK P minus trace of EKQ. You see? So I decompose it back. Now, nice thing here is, of course, you see here we have two positive things because this is a positive operator. So this quantity is always positive. This quantity is also always positive because Q is positive operator, right? So of course we can just upper bound this thing by changing the minus sign to a plus sign because this is bigger than 0. This is bigger than 0. In other words, this is upper bounded by trace of EK, yes, P plus Q. Sorry. Now, of course, here we don't need absolute value because everything is positive here, so they always get positive contributions. You see, and next thing is that, of course, I can just put, okay, let me just write it down, 1/2 sum of K, so if we put the trace here and EK here, times P minus P plus Q. Just put the sum inside the trace, and then this is replaced by identity. Okay, so finally the nice thing is that this is 1/2 trace of P plus Q. But actually, if you remember, P plus Q is precisely the thing where I just take all the minus eigenvalues of this and I turn them to plus. So this is exactly given by the trace of rho minus sigma. Is this step clear? I mean, you just have to recall how this thing looks like. It looks like we have the positive, so we have P minus Q, which are block diagonal. Now the absolute value is just P plus Q, right? Because all the negative eigenvalues become positive eigenvalues, so Q picks a plus sign instead of a minus, right? Is it clear?
Yep.
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 So in other words, now we just seen that what we've seen is that the classical trace distance, kind of which we constructed with some POM here, EK, it's always up. It cannot exceed our quantum trace distance, which is defined for two states, right? So which is already kind of nice. Now, next thing is, can we saturate this? This is the next question. Can we saturate this inequality? So is there a POM, in other words, is there a POM for which it's actually equal? So because if this is the case, then the maximal classical trace distance will be precisely this quantity, right? Because it's always upper bounded and it's obtained by some measurement. Yeah, and I'll just give you this POM, right? So remember that we have this P. So rho minus sigma, this is equal to this P kind of minus Q. If you can write like this, even so P also has zeros here, but you see what I mean, right? No, maybe it's not a good idea to write like this. Just put P minus Q, where P and Q are log diagonal. Well, which is also written here. Oh, this is stupid. Yeah, so this will just give you the POM. So consider the following POM. Do you have any guess for how to do it, or consider the POM with two outcomes, and this will be just projector on the P subspace and projector onto the Q subspace, right? And this projectors are now just given by 1 here, and 0 is here, and the other projector is well, the other way around, right? 1's here, right? I guess you can easily believe me that actually you can easily see that it's a valid POM, because with some of them we get identity matrix, and obviously they're just orthogonal projectors, so they're positive and do not exceed 1. Okay, so now let's just see what is the classical phase distance obtained with these projectors. So what we do to see this, what we do is we take yes. So what is this? D for this POM P Q of P on the two probability distributions. Well, this is just by definition 1/2, and we have the sum of trace of P, the projector P plus, times rho minus sigma, right? Check. So this is just P1 minus Q1, this thing here, right? So plus the other outcome. The other outcome is the one which corresponds to, so there is no sum here, of course, trace of P Q rho minus sigma. Okay. Oh, sorry guys. Somehow my okay. Yeah, again, we just replace this with our P and Q, and this becomes 1/2 trace of P projector on the P block times P minus Q plus 1/2 trace projector on the Q block P minus Q. And obviously, this thing is just equal to trace of P, right? Because when you project Q on the block P, we just get 0, right? Because Q has all its weights on the second block there, right? So just recall P is things here, lambda plus here, and 0 here, and projector P is 1s here, and 0 is here. So if you take the Q thing, then it has things here, and the projector is on 1 here, so it's 0, right? Am I saying obvious thing, right? Are you following?
Yep.
Yep.
Okay. So this is this, and this is 1/2 trace of Q. Yes. So in other words, this thing is simply trace of P plus Q, right? And this is, as we've seen, 1/2 trace of the absolute value of rho minus sigma. So we have proved what we wanted. Yeah? In other words, that what we've proven is that for this precise POM which we defined, D for this POM P and PQ, or P and Q, is exactly equal to the trace distance between the quantum states. Okay, which is nice. So in other words, another way. So we define this trace distance formally, right? By just taking the density matrices and tracing the absolute value. But we could also alternatively define. So alternative definition. Alternative definition is that D of rho and sigma then is just equal to the maximum kind of maximum. So the best possible classical distance obtained with all possible POMs, right? Of P and Q, and the maximization is over POMs, right? So we could also define it in this kind of not closed form, where we just say, okay, just look for the best possible measurement, which allows you to distinguish the two states, right? And then use it and define this quantity like this. However, we just see that it's actually can be just defined in a closed form with a trace of 1/2 trace of rho minus sigma. So it's very nice that we can have this sort of geometric distance on the set of density matrices, gives you a very nice interpretation as the best possible way to distinguish them, the two states, right? So if you recall now again about our example where we had the state of the probe at time t, which could be in two different states depending on the value of the magnetic field. Well, now in principle you know what to do, right? So the best possible measurement now will be exactly given by this p, by this two outcome QM, right? The projectors. Okay. And the guessing probability will be related to the trace distances before. So let me just write it down. The summary. So now we say that so interpretation. So D gives the best probability to guess the state, right? In the same way. So now we have P correct, just as before, is equal to 1/2 of 1 plus D between rho sigma. And now we have this optimal measurement. So we should have optimum, we have just constructed the optimal measurement. Wait. Sorry. So optimal measurement is precisely given by this P, two outcome PUM and PQ. And moreover, just if you wonder, so when if you observe, PQ, PP, you bet on rho, right? And observe the other one. So that if you observe the outcome which corresponds to the PUM element PP, you will bet on rho, and the other one, of course, you will bet on the other state, sigma, right? So it's kind of nice. Again, we start with some kind of geometrical definition, right, of the distance on the state of space, and then we recover a very nice interpretation, which is very useful in practice, right? This is kind of for hypothesis testing. You have two possibilities. You just quantify how well you can guess by this distance, right? So now we have what, 20 minutes left. So I think it doesn't make sense to start fidelity, but we can see some property of this trace distance, right? So first thing, which is very important and nice, is processing inequality. So let me just call it properties of D. Okay, so properties of D. Okay, so the first one, which is really nice, is the processing inequality. If I say processing inequality, does it mean something to you? What do you expect from hearing this? No guess? Well, it's kind of information theory. Processing inequality just means that by doing post-processing, you cannot increase something. Okay. So in other words, this means that so if I start with our two states, rho and sigma, right? In principle, what I can do is to apply some evolution there. Okay. So I can apply some map epsilon, right, and get epsilon rho. Of course, I don't know which one, so I have to apply the same exact map, right? Now, the question is, do you think I can increase the trace distance between the two states by doing this? What do you think?
I don't think we can.
Yes, it's true. Any intuition why? I mean, yeah.
Well, because we acted with the same map on both states.
Exactly. Yes. So, I mean, okay. Maybe it's. Okay. Let me just. So just let me write it down. So indeed, we cannot. So basically, this is precisely the processing inequality. Just states that the distance of these two states cannot exceed they can only get closer, right? So if you cannot exceed the original trace distance, this is the process inequality. Okay. Of course, it can get, so they can get closer. This is very easy. What you can do is one processing is just throw them away and replace them with something else. Then you get zero distances then, but they cannot be more distinguishable. And I think the easiest, so we could prove it formally, but the easiest way to see it is that we have two definitions for the trace distance. One definition is, is this geometric definition. The other one is do the best possible measurement. Okay. So in other words, we have, so how does it define? So we have rho or sigma, right? And now here we do kind of the best possible measurement. We get P or Q, okay? So we take, so this is our definition, right? So we maximize, so max is some kind of, the trace distance, one way to define it would be to kind of take these two states, look through all possible measurements we can do, and find the one for which the trace distance is, the classical trace distance is maximum, okay? But of course, what you can do now is one other possible measurement is just kind of you take this map here, epsilon, right? And you just do it before doing the measurement, okay? Now, kind of the thing is, this combination of the composition of these two, it just defined another measurement, right? You didn't increase the space of possible measurement. This was already possible to do before. What you can do this way. But do you see what I mean? So when we maximize over all possible measurements, one possible measurement is actually already do the channel and then do some other measurement. So this is already included. All these possible maps are already included in the maximization, because physically all possible measurements include do some channel and do a measurement, right? So kind of with this definition, it's basically self-obvious that the persistent inequality holds. Right? Is it clear? Or?
Yes, it's clear.
It's clear. At least for one of you, it's clear. Yes. So which is very nice because it means that kind of physically it's very relevant. You expect something to it like this to hold for a good physical distance that you cannot increase it with post-processing. At least in if you want to do some statistics with this. Okay, so this is one property. Then there are a bunch of other properties like convexity. Let me just maybe, if you probably are going to use the joint convexity. Maybe just, I'm not sure we need convexity so much in the following. So maybe we can just, the best thing to do now, I guess, maybe is to just see. First thing, let me just look on the note, is to see what this, to get some intuition, we'll just apply this to qubit states, no? And then just see what it means. So let's do this. Right, so to get some intuition, we'll just compute some trace distances for qubit states. Mm-hmm. Does it sound good? So qubit example. Yes, so for qubit states, of course, we have our nice block sphere. Right? And then we know that we can express any state, so rho, we'll just express it as some vector v times the vector of Pauli's. Okay? So you remember this, I guess? And sigma, we'll just express it in some other vector. Plus w times sigma. Mm-hmm. So in other words, on the block sphere, we just have this, the states are presented by two vectors, like v, for example, and I don't know, w here, inside the sphere, or on the sphere. Okay? Depending on the mixed or not. So let's just compute the trace distance between these two states. It's not difficult. So d of rho and sigma. This is 1/2 trace of rho minus sigma. In other words, it's just 1/2 trace of, 1/2. Let me just write it explicitly. Sigma. Okay. And well, it's now, so the identities are gone here. for the other vectors, we just have the difference of the vectors. So in other words, this is 1/2 trace of 1/2 V minus W times the vector of the Pauli matrices. So 1/4 trace of right. Okay, so now what is the absolute? So what does this look like? We have now a vector times my matrix, vector of Pauli matrices. So what is the eigenvalues of this object here, of this small matrix here? Do you remember this? Or we can do it again. Okay, well, let's just do it then. So let's look on this. So okay, we have, write it down. This is D of rho sigma, right? Okay, so now we have this operator here, D. So let's put this vector like put the delta times sigma, right? So first I can check that this is trace of this is equal to 0, right? Because this is equal to, because trace of all powers is 0. So it means that basically it has two eigenvalues, it's a remission, so it has two eigenvalues. In other words, in some bases delta sigma, it has two eigenvalues lambda and minus lambda, right? Because it's 2 by 2 matrix, so it only has two eigenvalues. Okay? Finally, we can also compute trace of the square easily. Delta times sigma squared. And this is equal to sum of delta I sigma I for I equal 1 to all the three Pauli matrices, right? Trace times sum of j, delta j sigma j. And you remember that the Paulis, they are orthogonal. So this is just equal to sum of delta I square. Yes, sum of delta I square. On the one hand, on the other hand, this is also equal to lambda 1 square plus lambda 2. So lambda 1 plus minus lambda square. So it's also equal to 2 lambda square. So in other words, we see that this thing, right? So lambda is equal to what? 1/2. Lambda is equal to 1/2 norm of the delta vector, right? So, you agree? Is it correct? Check, 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 check. So, in other words, this thing here is delta times sigma. This is just lambda, lambda, right? So in its trace, it's just 2 lambda. But I don't like this 2 here. Yeah, sorry, yes. Of course, the trace of the Pauli squared is 2. Okay? But we have 2 here. So there is no need to 2. So lambda is equal to. You get this? Yeah. Oh. Sorry. Okay, just finally, this is just another Pauli in some other basis, rotated, right, with a vector, and the trace of this thing is, as we just tried, I tried to do it now, but kind of it was a bit confusing, I guess, because it was too quick. They're just equal to 2 times the norm of the delta vector, which is V minus W. Okay, so in other words, the trace distance of 2 qubit states. So trace distance of 1/2 identity plus V sigma 1/2 identity minus W plus W sigma. This is equal to 1/2 norm of V minus W. Okay, so which has a very easy geometric interpretation, right? It's really just the trace distance is really just 1/2 of the distance between the two vectors here. So in particular, the probability of guessing, as we've just seen before, is equal to 1/2 1 plus 1/2 v minus w. So I guess you see when is it equal to 1? Any idea? Right, this. So this probability, you can guess them certainly in a single shot, only if this thing is here equal to 2, right? And this is equal to 2, so p guess equal to 1. This implies that v minus w is equal to 2, and this just means that they are really opposite points on the block sphere. Yes? Any two opposite points on the block sphere. I know, is it clear that this is opposite point? For example. Right, which is something you know already, I guess. Because this has a two, so the only kind of, if you have a state here, the only orthogonal state to it, in other words, the state which we can discriminate perfectly from the other one is the orthogonal state, which is just in the opposite of the block sphere. And of course, we can also now see, for example, what is the like if you have a z state plus z here, right? What is the probability to guess x? It's also just given by the distance, which is, I guess, something like 1 over square root of 2 or something. 2 times. Okay, no, it's not so easy, but so we can play with this to see how it works. Right. So yes, let me see if I wanted to tell you something more in the lecture. I think that's it, because it doesn't make sense to start fidelity now because it's quite long. Yes, so I guess since we had also 5 minutes longer last hour. So for the exercise, I think a good idea would be to, now you remember the problem we had in the beginning of the last hour? It was we have these 2 qubits and we want to see how to measure the field, if it's there or not. So you can just do this at the exercise, right? And now you know the tools we need, so you'll just need to compute the trace distance between the 2 states at the end. And then there are, of course, the question how to find the optimal time and how to find the optimal initial state. Does it sound like a deal?
Yes, it does.
Okay. Yes, so then it's it. And next time we will start with the fidelity and then move on to something else, like entangled states and so on. Right? Was it any comments on this video stuff? Shall I run bigger or no? Shall I speak clearer? Any suggestions?
I think it's okay.
It's okay? You could follow, or?
Yeah, sometimes it was a bit fast, but understandable in general. Yeah.
I also wrote a note, so I'll send you a note. So this time I had time to do it, but I'm not sure I'll always be able to do the right note because it's quite long. But yeah, hopefully.
Yeah, but with the recordings of the lectures, I think that should be enough.
Okay.
Oh, by the way, where are these